So let's assume we are given a data matrix X, just like the regular feature 1, feature 2, feature J, feature D, right? Sorry. Okay, point 1, point 2, so on and so forth, point 10. This is an N cross D data matrix, right, with Xi transpose here. I'm just writing it multiple times so that you'll not forget it. Okay, so this is my data matrix, right? For this given data matrix, there is something called a covariance matrix, often written as capital S. Let me define what covariance matrix is. So let me just define what covariance matrix is. We'll learn some very, very interesting properties of covariance matrix. So this covariance matrix is always of size D cross D. So given a data matrix X of size N cross D with D features, the covariance matrix for X, the covariance matrix X, extremely sorry. So this is called the covariance matrix of X. Okay, this is because X and S sound similar, I was getting confused. So the covariance matrix of X, of my data matrix X, is written as S, and it has D cross D. It's a square matrix. So this is called a square matrix because the number of rows and number of columns are the same. Okay, so the ith row and the jth column, this element is called Sij. Okay, so the element corresponding, so this is a matrix, right? This is a matrix with D cross D elements, right? D rows and D columns, right? So I'll write so Sij corresponds to the ith row and ith column element in matrix S. Okay, this is how I'll represent it, right? So let's take any value here. So again, we will come to it anyway. Okay, so this is how I'll represent it. Now let me define what Sij is as part of a definition. So Sij, okay, where I can go from 1 to D and J can also go from 1 to D because S is a square matrix of size D cross D. Sij is nothing but the covariance of feature I and feature J. Now let me introduce you some simple notation. Okay, so let me just erase this so that it becomes simpler. Okay, so whenever I say Fi or Fj, it means this column vector corresponding to the feature Fj. So whenever I say Fj, okay, whenever I say Fj, it is a column vector. What I'm referring to is it's a column vector. Okay, it's a column vector corresponding to jth feature. Okay, so take any element. For example, if I want to explain you about this element, let's say assume corresponds to ith data point. Okay, this is X, this corresponds to, let's say, Xi and jth feature. Okay, so this element I'll write it as Xij, just like Sij. Now here Xij, let me read it for you. Xij means, okay, so Xij means, right, it is the jth feature for the ith data point. Okay, simple notation here. I'm just introducing you to notation so that writing the math becomes easy. So Xij basically means for the ith point, I'm looking at the jth feature. And whenever I say Fj, it is basically the column vector corresponding to the jth feature. Okay, so since this is a column vector and this is a column vector, it's basically like your simple covariance, right? So we saw the formula for covariance when we learned about correlation coefficients, etc. Covariance between any two random variables X and Y, is nothing but 1 by n summation. This is nothing but the average. It's the average value of Xi minus mean of X, okay, Yi minus mean of Y. We saw this definition, right? We also saw how its interpretation geometrically, right? We saw its interpretation geometrically when we learned about correlation coefficients, Pearson correlation coefficients, Spearman rank correlation coefficient, and simple equation for covariance, right? We learned all about it based on the shape. We also saw its geometric interpretation. So covariance again comes back to help us. This is a concept that we learned in probability. It has connections to linear algebra. Okay, So let's understand it. So what I'm saying here is the ijth element of my covariance matrix is nothing but the covariance of fi and fj. I also know that covariance of fi and fj is nothing but the variance of fi. We also learned this when we learned covariance, right? Covariance of, or probably I would have written it like this: covariance of x comma x is nothing but the variance of x. Of course, if instead of y, if I put x here, this is nothing but the formula for variance, right? Nothing very fancy there. This is obvious. Okay, so let's understand our matrix again. Our matrix, oh, there is one more property for covariance, which is covariance of fi and fj is same as covariance of fj and fi. It's one and the same, because if I replace x's with y's with x's, this formula doesn't change, right? If I put yi minus mu of x, xi minus mu of x, it doesn't change, right? So covariance of, so these are some of the simple properties of covariance. Let's call this property 1 and property 2. The first property is covariance of x comma x is nothing but variance of x. The second property is symmetric, which means covariance of fi comma fj is nothing but covariance of fj comma fi. Now, having learned this, so what does our covariance matrix look like? All the diagonal elements. So it has d diagonal elements, right? It's a d cross d matrix, which means it has d diagonal elements. On the diagonal elements, you'll see variances of features. Okay, and since this matrix, so let's assume this is Sij and this is Sji, right? Since Sji and Sij are the same, so this matrix is also called symmetric matrix. So let me write a very simple symmetric matrix. What is a symmetric matrix? If I have a matrix like this, let's assume 2, 1, 3. Okay, these are called my diagonal elements. I'll write a 3 cross 3 matrix here just for simplicity, so as to explain it to you. Okay, so let's assume I have 1 and 2 here, and let's assume 5 here. Okay, so if this is 1 and this is also 1 and this is 2, and let's assume this is 5. Sorry, did I write it well? 2, 1, 2, 2, 1, 2, 1, 1, 5, 1, 1, 5, 2, 5, 3, 2, 5, 3. Yes, this is called a symmetric matrix because, so take this element, right? This is first row, second row, third row. This is first row, first column, second column, third column. So take this element. What is this element? This element is, so if this matrix is A, this is A, 2, 1, second row and first column. If this is equal to A, 1, 2, what is A, 1, 2? First row and second column, this element, they're same, right? If Aij is equal to Aji for all I comma j, okay, then we call it a symmetric matrix. In this matrix, since Sji equals to Sij, right, here look at it like this. This is 3, 2, third row, second column, right? So A32 is 5. What about A23? A2 second row, third column is also 5. So as long as it is satisfied for all, as long as this condition is satisfied for all I comma j, of course for diagonal elements ai is, so all your diagonal elements will look like what? S11, S22, S33, S44, so on and so forth, SDD, right? So this is called a symmetric matrix, a matrix where Aij, a matrix A is called a symmetric matrix if Aij equals to Aji for all I comma j. Now your covariance matrix is also a symmetric matrix, because by definition, because since Sij, what is the definition of Sij? Sij is covariance of fi comma fj, which is equal to covariance of fj comma fi from this property 2, which is equal to Sji. Since Sij is same as Sji, your S is also a symmetric matrix. It's also a square matrix. Why is it a square matrix? Because the number of rows, because it has d rows and d columns. Same number of rows and columns is called square matrix. Same number of rows and columns. So this is called a square symmetric matrix. Okay, your covariance matrix is a square matrix and also a symmetric matrix. Okay, so we understood the definition of covariance matrix, right? We'll see why it is useful. Bear with me. We're just defining terms here. We're not doing anything very, very fancy here. We're just defining a bunch of terms. Okay, now let's understand some very, very interesting property. So let's assume my data set X, which has D features, right? F1, F2, so on, so forth, D features. And I have points 1, 2, so on, so forth, N. It's an N cross D, right? Let's assume, let's suppose that X has been column standardized. So what does column standardization mean? It means that the mean of any of my FIs equals to 0, and the standard deviation of any of my features equals to 1. That's what it means, right? We just learned about. Let's assume X has been column standardized. Okay, let just bear with me. Then what is the covariance of feature Fi and Fj? Let's write the formula, right? Okay, so so if I have two features Fi and Fj, what is the covariance between them? Okay, so let's write it down. So let's assume this is my Fi feature and this is my Fj feature, right? Okay, it has elements, right? It has x1i, x. So what is this element? This is x first data point and ith feature. What about this? This is x2 second data point, right? It corresponds to second data point and ith feature. Similarly, this one is x1 jth feature. This one is x2 jth feature. We just learned about this terminology, right, a while ago. If you look here, I just explained xij terminology here. I'm just reusing that right now. Okay, so covariance of Fi and Fj is nothing but 1 by n summation over 1 to n. Okay, so let's write it. So what are the terms here? They are x I. Okay, let me call it F1, F2 just for simplicity. Okay, so let's assume I want to find the covariance between, let me just erase this so as not to confuse the, so as to make it simpler. Covariance of F1, F2 is nothing but xi1 minus mu1. I'll define what mu1 is, just bear with me. xi2 minus mu2. Now mu1 is nothing but the mean of f1, sorry. This is nothing but mean of f2, right? So let me change the color so that I can explain it better. Okay, so I have two. So this I can think of as my random variable x. This I can think of as my random variable y. What is the covariance of x comma y? Take all the values of x, subtract the mean of x, take all the values of y, subtract the mean of y, right? And take the average value. This is basically averaging, right? Exactly. So these are all my values for my random variable. My random variable here is my feature, right? My random variable here is my feature. So having said that, let's go into it. So xi1 corresponds to, so okay, let's do it. Suppose if this is my f1, if this is my f2, okay, I just write it much more cleanly. Let's assume this is my data set x. Okay, so what will this be? This will be x1. This is my first data point, right? x1, 1. So what I'm doing here is I'm taking all the values of these features, each of these individual values for this feature. Let's assume this feature is petal length, and let's assume this feature is petal width. Let's just assume. Okay, so I'm taking each of the petal widths in my data set, subtracting it with the mean petal width. Okay, that value I'm multiplying with each of the petal widths, subtracting with the mean petal width. This is the petal length. Let's say these are petal lengths. This is the mean petal length. Let's assume this is petal width. This is the mean petal width from our iris dataset example, just so that you connect the dots. Now, one thing you know is since your data has been column standardized, okay, these means are 0, this is 0, and this is 0, right? So what happens to my covariance of F1, F2? I can write my covariance of features F1 and F2 as 1 by n summation I equals to 1 to n xi1 and xi2 multiplied by, because this has become 0, so this goes away, this has become 0, it goes away. So I'm just left with this term and this term. So what does this mean? Let's understand what it means. Let me draw my data matrix much more clearly. Suppose this is my data matrix. Let's assume this is my feature 1 and this is my feature 2. Okay, this is my feature 1 and this is my feature 2. Okay, of course I have lots of features like this up to FD. This is my first point, my second point, my third point, fourth point, so on and so forth, n points. Okay, this is my first observation corresponding to my first data point for feature 1, again for feature 2. Okay, my second observation. So what this is saying here is multiply this value with this value. Okay, again multiply this value with this value, multiply this value with this value, so on and so forth. That's what it is. What is xi1? Right, xi1 is for the ith point. This is xi1, this is your xi1, this is your xi2. It's saying multiply xi1 with xi2, which means multiply these two and sum up from I equals to 1 to n. So what am I literally doing? I'm basically multiplying my f1 with f2. I'm doing a dot product between f1 and f2. That's what this sum will be equal to. So I can write that my covariance between f1 and f2, can I write it as f1 transpose f2 multiplied by 1 by n? Because what is f1 transpose f2? Okay, what is f1 transpose? Basically, instead of a column vector, I'll make this a row vector. I'll take this vector here. Okay, I'll convert this into a row vector and I'll multiply with this column vector. Right? Whenever I multiply, we learned this in basics of linear algebra. If I'm doing component-wise multiplication, if I'm doing component-wise multiplication, and if I'm adding up all of them, that is nothing but dot product. This is nothing but the dot product between f1 and f2. What is dot product between f1 and f2? Component-wise multiplication followed by addition. And what is the formula for f1 dot f2? It's nothing but f1 transpose f2. Right? So you can say that if your features are, if f1 and f2 have been standardized, right, then covariance of f1 and f2 is nothing but f1 transpose f2 by n. Literally, that's what it is. Okay. Now let me argue something much more interesting now in a second. My argument is as follows. Okay. Let me fill it for you. Let me fill the argument for you. I will argue that my S, my covariance matrix, my D cross D matrix is nothing but I'll take my matrix X, transpose it and multiply with matrix X. Now, what is the size of matrix X? My data matrix. This is my data matrix. This is my data matrix. This is my transpose of my data matrix. This is n cross D. So this will be D cross n. So when I multiply these two, what will I get? I'll get a D cross D matrix, which is what S is. Okay, but let me prove that each element of S will also work out. Okay, so here I'm assuming, remember I'm assuming that X has been column standardized. I'm assuming this. This is a very important assumption that we cannot rule out. Okay, so let's see what is Sij. What is Sij supposed to be? It is covariance of feature I and feature j. Oh, sorry, I need to put a 1 by n here. Sorry, I forgot that. Okay, so we learned from the formula earlier. Let's look at the formula. What is the definition? Not the formula. Sorry. What is the definition of okay? Here is the definition. What is the definition of each element of Sij? It's nothing but covariance of feature I and feature j. Right? Now I know. Okay, coming back to our discussion, I know from this formula, I know that covariance is nothing but f1 transpose f2 by n, right? So this is nothing but fi transpose fj by n, right? Now, so this is your LHS. Think of this as your LHS. I'll prove that the ijth component of your RHS is exactly this. Okay, let me show that to you. Okay, what does x transpose x mean? Okay, this is important to understand. Okay, if this is X transpose and this is X, what is F? What is so for this whole matrix, I want to understand what is the ijth component of this multiplied by this, right? I want to understand the ijth component. When will I get the ijth component of this product? When I multiply the ith row, when I multiply the ith row with the jth column, sorry, when I multiply that with the jth column, right? When I multiply with the ith row and jth column, and when I add, so when I multiply this with this, when I multiply this with this, and when I add it, this is simple matrix multiplication, right? Those of you who have learned basic matrices in your high school or in undergrad will quickly understand this. This is basic matrix multiplication. So your ijth column of this multiplication, so on LHS, we know that Sij is nothing but Fi transpose Fj by n. Okay, let's look at our RHS. Okay, our RHS, I need to prove that this multiplied by this, the ijth column of this multiplication is nothing but Fi transpose Fj. I'll prove that to you. So I know that the jth column in X is nothing but Fj. Okay, so this for the ijth value of this this multiplication is nothing but Fj multiplied by, okay. Since I've transposed this matrix, what happens? My columns become my rows here. That's what transpose is, right? This is X transpose. This matrix is X transpose. What does transpose mean? My columns become my let me change the color here. My columns become my rows here. So what is the ith row here? My ith row is nothing but Fi transpose. So the ijth value for this multiplication is nothing but Fi transpose. Sorry, let me write it more appropriately. Sorry. My ijth value of this multiplication will be Fi transpose Fj. Okay, which is what we wanted to prove, right? So your Sij is nothing but Fi transpose Fj by n. This is your LHS. Even on your RHS, this is your RHS, right? Your RHS, what do you have? X transpose X. For your X transpose X, when I multiply it, the ijth value of this product will be Fi transpose Fj. So yes. So what I have here is on the RHS, on the LHS, I have Fi transpose Fj by n. On the RHS, when I multiply this whole thing by n, because the formula here, I said S is nothing but 1 by n into X transpose X, right? So on my RHS also, I have exactly the same thing. So my RHS equals to my LHS, which basically says that my S is nothing but X transpose X, when X is represented the way we showed. And this is a D cross N matrix. This is an N cross D matrix. It's always good to write this so as to understand whether you can actually multiply these matrices or not. Okay, so you can get your covariance matrix again if X has been column standardized. Otherwise, this formula doesn't hold. We will use this formula a lot when we are learning. We'll use this extensively when we are learning about when we're trying to do dimensional reduction using PCA. This is extremely important. So your covariance matrix is nothing but X transpose X if your matrix X has been column standardized.